Alright, in this video we study an application of the kernel method to the polynomial regression problem. So we are given a set of data points which are pairs of real numbers, x and lambda. And what we want to do is to approximate the value of lambda by some polynomial of x of the degree of at most d. When the degree d is less than n minus 1, when n is the number of data points, using the kernel defined as this one, we can find that the optimal polynomial is given as a linear combination of the reproducing kernels, like this. Okay, let's start. But before studying this case, we study the other case, that is when the degree d is greater than or equal to n minus 1. For this case, we don't need the kernel method because these equations can be solved exactly. But nevertheless, it is instructive to study this case first because some of the results obtained along the way can be reused later. Okay. First, suppose all the values of x's are distinct. x1, x2, and so on, xn are distinct. That means each of them is different from all the others. Then there exists a polynomial. Let's say p of x, c0, c1x, and so on, up to cn minus 1, x to the power of n minus 1. So the degree of this polynomial is less than or equal to n minus 1, such that for each j, we have lambda j equals to p of xj for j from 1 to and so on up to n. Okay, so let's prove this. So if we write this down explicitly, we have the following simultaneous equations. So for lambda 1 is equal to c0 plus c1 x1, c2 x1 squared, and so on, plus cn minus 1 x1 to the power of n minus 1. And similarly for lambda 2, we have c1 x2, c2 x2 squared, and so on, cn minus 1 x2 to the power of n minus 1, and so on. And finally, we have lambda n equals to c0, c1 xn, c2 xn squared, cn minus 1 xn to the power of n minus 1. And using the matrix vector form, we can represent these simultaneous equations more concisely as follows. So we have lambda 1, lambda 2, and so on, lambda n. This is a vector. And the matrix will be 1, x1, x1 squared, and so on, x1 to the power of n minus 1, 1, x2, x2 squared, and so on, x2 to the power of n minus 1, and so on, and xn squared, xn to the power of n minus 1, and c1, c2, and so on, cn. And this vector of lambda is a known vector because all the values of lambdas are known. And this vector of c's is unknown because we want to find these values of c's. And this matrix consisting of x1, x2, and so on, this is a known matrix because the values of x's are given. Okay, so whether the solution to this equation exists or not depend on whether this matrix is invertible or not. But this matrix is a very well-known matrix called the van der Monde matrix. So let's call it V, and then the determinant of V is given as this. It's the product I less than j and x xj minus xi. So it's the product of the differences between two different values of x's. Okay, so this is non-zero if all the values of xi's, xj's, they are distinct, and which is actually our assumption here. It is distinct values. So this matrix is invertible, and therefore the solution to these simultaneous equations exist. So we are done with the case where d is sufficiently large, that is greater than or equal to n minus 1. So now let's move on to our main topic where d is less than n minus 1. So let us first define the set of polynomials PD with degrees of at most d. So this is a set of polynomials such as c0, c1x, and so on, plus cdx to the power of d, where cj's are real numbers, j from 0 to d. So we have d plus 1 coefficients, so unknowns. And we have n data points, so we have n simultaneous equations. And we're assuming this, so d is less than n minus 1, so that means d plus 1 is less than n. So we have more equations than constraints than the number of parameters. So this problem is in general unsolvable. So what we do is to minimize the error function. So that means we define the error function of the polynomial p as this. Sum of j from 1 to n and polynomial p of xj minus lambda j squared. So we minimize this error function with respect to p. So let's say mean of LP, and p is an element of this set PD. So we want to do this minimization problem. We have seen in the previous video that this minimization problem can be solved using the kernel method. So this is equal to the norm squared of this. K, this is a matrix made of kernel functions, and C, which is a vector of coefficients, minus lambda as a vector. And so this K is a matrix made of the values of kernel functions. K is a kernel function, and X, I, X, J. So this K is a kernel function, and Xi, Xj, they are given data points. So the ij element of this matrix is this. And C is a set of coefficients. So C1 to Cn. So it's an n-dimensional vector. And lambda is the vector of lambdas, which is also a given data. So here we are assuming this p of x is a polynomial function. For that, what kind of kernel function should be given? It turns out that our kernel function should be of this form. K of x and y is equal to 1 plus yx plus y squared x squared, and so on, and y to the power of d times x to the power of d. And as usual, we write this bivariate function k of x and y as a parameterized univariate function k y of x. Then our optimal polynomial function would be of this form. That is a linear combination of j from 1 to n and kxj of x. So since we are adopting this kernel function, this is a polynomial function with a degree of at most d. So this looks all right, but there are a few questions to be answered. First of all, is this function really a kernel function? As a kernel function, it has to be symmetric and positive semi-definite. Symmetry looks quite obvious from this form. So if you swap x and y, we still have the same function. How about positive semi-definiteness? Well, actually we can prove more easily than proving that directly, because for any function f of x, if we define k of xy as f of x times f of y, we have seen that this is a kernel function, right? So yx, y squared, x squared, they are all kernel function. Of course, 1 as a constant function is a kernel function. And we have also seen that if we have two kernel functions, k1 and k2, if k1 and k2 are kernel functions, their sum is also a kernel function, as we have shown in the other video. So the sum of kernel functions is a kernel function. Therefore, this k of x and y, as we define here, is a kernel function. And the next question is whether the polynomial functions as defined in this way, that is, wait a minute, it's a linear combination of k xj's, okay? So this cj comes from this cj here, okay? This c, okay? So does this kind of polynomial functions cover entire space of all possible polynomial functions with a degree of at most d? So that's the next question. So if that's not the case, then if we are only considering a subset of all possible polynomials, that means the polynomial function obtained in this way may not be really the optimal one. There can be some other optimal function, but we'll show that is not the case. So this covers actually all possible polynomial functions with a degree of at most d. Okay, let's show that. And it suffices to show the following theorem. So that is y1, y2, and so on, and up to y d plus 1. So these are real numbers, are all distinct. That means each of them is different from all the others. Then the corresponding reproducing kernels, that is ky1, ky2, and so on up to ky d plus 1, are linearly independent. Okay, let's show this. To show this, suppose a linear combination j from 1 to d plus 1, cj k y j is equal to 0. And we show that all these cj's are 0 in the end. So we have, if we evaluate this function at x, we have j from 1 to d plus 1, j1 k y j of x. And remember, this one is equal to k of x, y, j. And using our definition of the kernel function here, this kernel function is cj and sum over of I from 0 to d and yj to the power of I and x to the power of I. And rearranging the sum here, we have I from 0 to d and j from 1 to d plus 1 and cj yj to the power of I times x to the power of I. Now, by assumption, this here means this function is identically equal to 0. So whatever the value of x is, this is equal to 0. So as a function of x, this is identically equal to 0, which means each of these coefficients is 0. So that means sum j from 1 to d plus 1, cj yj I is equal to 0 for each of I equal to 0, 1, and so on up to d. Now, let's write this down more explicitly for each value of I. When I is equal to 0, we have C1 plus C2 plus and so on up to CD plus 1 equal to 0. When I is equal to 1, we have C1 Y1 plus C2 Y2 plus and so on plus CD plus 1 YD plus 1 equal to 0. When I is equal to 2, C1 Y1 squared, C2 Y2 squared, and so on, CD plus 1 YD plus 1 squared. And this continues up to I equal to D. So C1 Y1 to the power of D, C2 Y2 to the power of D, and so on, CD plus 1 YD plus 1 to the power of D equal to 0. So we have these simultaneous equations. Now, let's represent these equations in matrix vector format. So that becomes this. So the matrix part will be 1, 1, and so on, 1, and y1, y2, and so on, yd plus 1, and y1 squared, y2 squared, and yd plus 1 squared, and so on, and y1 to the power of d, y2 to the power of d, and yd plus 1 to the power of d. So that's the matrix part. And the vector part will be C1, C2, C3, and so on, CD plus 1, and which is equal to the 0 vector. Now, this is a D plus 1 by D plus 1 matrix. And we are assuming that all the values of y's are distinct. That means, and also notice that this is a van der Waals matrix. Again. So its determinant here, let's call it V, or maybe we should call it transpose of the van der Waals matrix or whatever. So its determinant is this product, I less than j and yj minus yi, which is non-zero. That means this matrix invertible, and if we invert this matrix, the right-hand side is the 0 vector. So that means this vector, c1, c2, and so on, cd plus 1, this is a 0 vector. And that was what we wanted to show, and we are done. So after all, as long as the values of y's are distinct, the reproducing kernels k, y1 up to k, y, d plus 1, they are linearly independent. Now consider the space of polynomials represented as a linear combination of these reproducing kernels, Cj and Kyj, where Yj is any real number and Cj is also any real number. Okay, j from 1, 2, and so on. So consider only finite sum. Now it doesn't stop at d plus 1, but it may go beyond d plus 1. But anyway, it's a finite sum. And this is a space of polynomials with a degree of at most d. So the dimension of this vector space V cannot be greater than d plus 1. And as long as yj's are different, So these are linearly independent. So the dimension of this space V is actually D plus 1. Okay? And recall, we define this space of polynomials with a degree of at most D. So the dimension of this space is also D plus 1. So their dimensions are the same, and they are both spaces of polynomials. So therefore, we can conclude that PD is actually V. So all of the polynomials with a degree of at most D can be represented as a linear combination of these reproducing kernels. And we can introduce an inner product in this space. So let's say f and g are polynomials with a degree of at most D, then they can be represented as a linear combination of the reproducing kernels. So let's say f is ai times k xi, and g is linear combination of this bj and let's say k yj. Okay, then we can define their inner product, PD, as this. Sum over I and j, ai, bj, and k, yj, xi, and using this kernel function. And we have seen before that for any kernel function, thus defined inner product is indeed an inner product, satisfying all the axioms of the inner product. So this induces a reproducing kernel Hilbert space, which is also a completion of the space of polynomials. But actually, we don't need this completion process because we are only considering a finite space, finite dimensional space, so they are actually the same thing. So for any polynomial, let's say p of y, a0, a1y, and a d, y to the power of d, then we can write this polynomial as some inner product. So p and k, y. So according to the general kernel regression technique, then the optimal polynomial that approximates the given data sets is given as this: p of x as a linear combination j from 1 to n is the number of data points, some coefficients cj, and the kernel function k and xj of x, which is equal to, equivalently, of course, k of x and xj, which is, so if we write this kernel function more explicitly, this is equal to cj 1 plus xj x plus xj squared, x squared, and so on, xj to the power of d, x to the power of d. So if we factorize by powers of x, then this becomes j cj and j cj xj x j cj xj squared, x squared, and so on, and j cj xj to the power of d, this. So these can be some constant, and finally we have something like this: a d x to the power of d. So a0 is equal to this sum, a1 is equal to this sum, and so on, and ad is equal to this sum. And of course, these coefficient c's, these can be obtained by minimizing this kc minus lambda. So just using the usual linear regression problem or the least squares method, we can find this vector c very easily. Okay, that's all for this video. See you next time. Bye. Thanks for watching. If you like this video,
Please hit the like button and subscribe to this channel. See you next time. Bye.